For 20 months, the skies were empty of Boeing's flagship aircraft. Following two catastrophic crashes that claimed 346 lives, global aviation authorities grounded the entire Boeing 737 MAX fleet. It was an unprecedented halt in modern commercial aviation. But the root cause of this massive grounding wasn't a shattered wing, a structural defect, or an explosive engine failure. It came down to a single piece of data, fed from a single sensor into a software system that most pilots didn't even know existed. This is the story of how an engineering compromise and a flawed certification process brought down an aviation titan, and why a single point of failure was allowed to override human control. To understand why this system existed at all, we have to rewind to 2011. Boeing's primary competitor, Airbus, had just announced the A320neo, a highly efficient update to their popular narrow-body jet. Facing immense pressure from airlines demanding better fuel economy, Boeing had to respond quickly. Instead of designing an entirely new airplane from scratch, Boeing decided to update their workhorse, the 737. They called it the 737 MAX. But there was a physics problem. The new fuel-efficient engines Boeing selected, the CFM LEAP 1B, were significantly larger than the previous generation. Because the 737 sits notoriously low to the ground, these massive engines couldn't simply be bolted underneath as before. Boeing's engineers had to mount them further forward and higher up on the wing. This physical change fundamentally altered the aerodynamics of the aircraft. Under specific manual flight conditions, the new engine placement created additional upward lift. The aircraft naturally pushed its nose higher. To get the 737 MAX certified, Boeing needed it to handle exactly like older models, so pilots wouldn't require expensive retraining. Their solution wasn't a physical redesign, it was a software patch. That software patch was named the Maneuvering Characteristics Augmentation System, or MCAS. Its job was simple: automatically apply nose-down trim to the horizontal stabilizer when the aircraft sensed it was pitching up too aggressively. In theory, MCAS would make the MAX feel identical to older models, operating quietly in the background. But the implementation contained a fatal engineering flaw. The original design of MCAS relied on input from just a single angle of attack sensor at a time. This sensor is a small blade on the fuselage that measures the angle between the wing and the oncoming air. Commercial aircraft are built on the principle of redundancy. If one system fails, another backs it up. But by wiring MCAS to trust a single sensor, Boeing created a single point of failure. If that one sensor broke or was miscalibrated, it would feed bad data to the flight computer, and MCAS would assume the plane was stalling. It would then automatically force the nose down, fighting the pilots for control of the aircraft. There was no backup sensor configured to check the math. Compounding this engineering vulnerability was a breakdown in regulatory oversight. The Federal Aviation Administration had increasingly delegated safety certification responsibilities directly to Boeing through a program called Organization Designation Authorization. Boeing was essentially inspecting its own homework. To keep the promise that MAX pilots wouldn't need new, expensive simulator training, Boeing systematically minimized the presence of MCAS. They omitted details and explanations of the system from the 737 MAX pilot flight manuals entirely. Pilots stepping into the cockpit had no idea that a background software system had the power to aggressively pitch the nose down based on a single sensor's reading. Behind closed doors, warning signs were flashing. In internal messages from 2016, Boeing's chief technical pilot, Mark Faulkner, explicitly noted that MCAS was acting erratically during simulator testing. Yet the system moved forward, and the planes were delivered to airlines around the world, carrying a hidden vulnerability. The theoretical risks became tragic reality off the coast of Indonesia. On October 29, 2018, Lion Air Flight 610 crashed into the Java Sea shortly after takeoff from Jakarta. The captain, Bavie Suneja, and First Officer Harvino fought a plane that repeatedly forced its nose down due to a faulty angle of attack sensor. Less than 5 months later, on March 10, 2019, Ethiopian Airlines Flight 302 commanded by Captain Yared Gatechu and First Officer Ahmed Nir Mohammed, suffered the exact same fate, crashing near Bishoftu. The subsequent investigations revealed a deeply complex web of failure and even sparked international disagreement. The Ethiopian Accident Investigation Bureau's final report blamed the crash almost entirely on Boeing's MCAS design. However, the U.S. National Transportation Safety Board and French investigators cited crucial crew operational factors as well. They noted that the pilots had left the engine thrust running exceptionally high, leading to excessive airspeed. This created such massive aerodynamic force on the tail that the pilots physically could not move the manual trim wheel to counteract MCAS. The software had locked them into an unwinnable physical battle.
The devastation of Flight 302 was the final breaking point. Global aviation authorities finally stepped in, overriding Boeing's initial assurances, and grounded the entire 737 MAX fleet worldwide. The planes would sit idle for 20 months while the full scale of the MCAS flaw was exposed and corrected. The corporate fallout was swift. By late 2019, Boeing's chief executive officer, Dennis Muhlenberg, was ousted by the board of directors as the company faced intense public and congressional scrutiny over its safety culture.
The tragedy of the 737 MAX is a stark lesson in the limits of engineering workarounds. Boeing attempted to solve a physical, aerodynamic hardware problem with a software patch, and then stripped away the foundational aviation principle of redundancy by relying on a single, unverified sensor. Combined with an environment of delegated regulatory oversight and a drive to protect the bottom line, it created a system designed to fail. It stands as a profound reminder that in complex, safety-critical systems, efficiency and cost saving can never replace transparency and rigorous, independent validation.